All right, welcome everyone. My name is Mark Grover, and I'm going to be here talking about building applications on Hadoop. I was told that Venkat has a session at the same time on Java 8 features, and I was secretly hoping no one would show up so we could go and just hear Venkat. But you're all here, so I guess we'll just stick to this. Cool. So I am Mark_Grover on Twitter. Follow me if you like what you see. If you don't like what you see, still follow me. All right, so the agenda for today is very simple, right? My expectation here is that most of you have heard about Hadoop. Maybe some of you have played around with Hadoop. Perhaps there are a few who have very little exposure to Hadoop. So I have 1 or 2 intro slides on what Hadoop is and why it's become so important in the industry. And then I have a whole bunch of other slides on what we are here for today, right? How do you write applications on top of Hadoop? In particular, how do you write Java applications on top of Hadoop? Cool. So this is my only slide on what is Apache Hadoop, right? So with a show of hands, how many of you have heard about Hadoop or played with it? Okay, I guess I don't really need this slide. Cool. So going through, 2 parts to Hadoop by default, the distributed file system called HDFS, and the default execution engine called MapReduce. Okay. There is a new precedent in the industry to have new execution engines. So you still use HDFS as your default base layer, which is this guy right here. But on top of that, instead of MapReduce, you put other executions on top of it, right? So the examples of that are Apache Spark, Impala, which is a SQL engine, Cloudera Search, which is also a search engine and its own execution framework. Anyway, 3 reasons why it's become very popular in the industry. It scales economically on the right there, which means if you have 10 times more data, all you do is increase your cluster size by 10 times, and that's it, right? You don't have to any longer invest in a single beefy piece of hardware and put more and more money in it. By the way, that gets exponentially more expensive as the demands on that piece of hardware increase. This is a distributed system, and all you do is you add more nodes, right? It's also flexible. That means you can store a variety of data, right? So you're no longer limited to a tabular row column format, but you can also store data that can be log data, that can be image data, that can be video data. So you have the flexibility to store a variety of data. And then, once you store a variety of data, you can't really do your traditional select count of this column from this table where this value is equal to that, right? That no longer is the only analysis that makes sense, so you need to be able to support more complex analysis. And so the third reason Hadoop has become popular is the ability to store more, to allow for more complex queries, right? So one is economics, the other one is flexibility, and right in the center is the complexity. Yeah? All right. Let's get to the fun part. So developing apps on Hadoop. Hadoop has a variety of use cases, right? I'll talk about a few of them because it wouldn't make sense for us to talk about how to develop apps on Hadoop without talking about what is it that people usually do with Hadoop, right? So the first very common use case of Hadoop is in data warehousing. So you're an organization, let's say you are a Forex trading company, right? Every day, clients come and they trade currencies on your platform, right? You track all these currencies as transactions in your transactional database, right? Maybe you have a web interface in front of this. At the end of the day, you want to look at the profitability of the company. You want to look at, are there people who are doing better than other people? Maybe we should have more people like them so we can make more money off of them. Regardless, right? So this is typical business intelligence queries where you look back at your data and do analytics on it within the domain of what your organization is. That is, I would say, the single most popular use case of Hadoop. The second most popular use case of Hadoop is something like fraud detection, right? You're a credit card company. You have a profile of a user. They say, this user is Mark, and this is a manifestation of Mark based on the transactions he's done in the past 30 days or the past year or the past 10 years, right? Depends on how much data you have on Mark. So now you have this profile. Every time I go swipe my credit card, if it's in Sweden or the US or Canada, They can figure out, based on my spending patterns, whether this transaction looks to be matching with that profile or not. So fraud detection is another example of a use case of Hadoop, right? The third common use case of Hadoop is clickstream analysis. So you are an e-commerce company. You've got a whole bunch of people coming to your website, clicking on a bunch of things, and maybe a few of them will buy something, right? Now, you get very interested in people who bought something. You want to know, where did they actually come from to my website? Did they read a blog post in the past 30 days? Did they actually do a Google search? Did they actually click on the paid link that I spend money on Bing every week? Did they click on that link, right? So maybe you want to optimize your marketing budget based on that. Okay, so 3 use cases, right? The first one, BI. The second one, fraud detection. The third one, clickstream analysis. By no means these are the only 3 use cases of Hadoop. These are 3 most common use cases of Hadoop. Okay, so how does that relate to the picture I'm showing you here? All 3 of those use cases have this picture-looking architecture, right? So on top you have this web application, right? By the way, red is user code, so you wrote this web application. And then we collect events from this. Blue is infrastructure, right? So there's some infrastructure you collect events. What's an event? It's a log line, right? At the very basic level, it's if you're a website, someone came, you have a log line in your Apache logs that says some dude showed up from this IP address at that time and clicked on this page, right? That's all you know. Maybe you have a cookie in that log line, but that's an event in this terminology, okay? All right, so the green stuff is data. You take this event, you put it in Hadoop, that becomes the green stuff all of a sudden, and then you do like some sort of job on it, right? You run a periodic job. This could be an hourly job, or every 5 minutes, or every day, or every month, whatever you want to do. You do analysis in this job. This is a job where you figure out, well, how many people came yesterday from this IP address and bought ski gear, right? How many people in the city of Stockholm came on last full moon night and bought coffee beans, right? This is the process that, again, you write. That's why it's user code for doing analysis, okay? Once you've written that, you create a new data set called reporting data. Now, this is the fun part. Reporting data will be used in all further analysis. So now, if you are the BI team, you build an application on top of this. Maybe you plug in your BI tool like Tableau, and the management gets to see all the analysis that's there in this aggregated data set, right? If you have a recommendation system, so if you're a LinkedIn, you want to provide recommendations to LinkedIn and say, you know Mark, you may also know Mark Zuckerberg, right? And that kind of recommendation is also built on this aggregated data, right? So this data can be used in other applications, can be queried directly by BI analysts. It obviously sits in Hadoop because it's the green thing, but you can also make a copy of this in other production databases or connect those databases to Hadoop. That's outside the context of this talk, but this is a general sort of architecture that most applications follow. Clear there? Okay, so zoom level 100 to 1 because I'm talking about a very big level, right? Okay, so what we have realized so far is Hadoop's really powerful, right? You can do a lot of different things with just one piece of software. That's primarily the reason why it became just so disruptive in the industry, okay? We've also realized it's very flexible, right? You can store images, you can store logs, you can store row column stuff, you can store videos. If you're a Netflix, you can track how many people come, see which video, when do they pause, do they click on ads, when do they resume, how many times did they pause, is there a correlation between if they see an ad and buy something, right? So it's very flexible, but it's incredibly low level, all right? And that's where the problem starts. You can't really provide flexibility in a very new product. Hadoop's been around for, well, the paper was written in 2004, so it's almost coming to 10 years. But the open source Apache Hadoop has probably been around for 5-6 years, right? So it's very low level. The developers who are writing applications on top of Hadoop need to know a lot of infrastructure details in order to make sense of it, okay? And it's incredibly complex, okay? I can't come and say, I've done typical database application sort of thing before in my past, connecting to databases over JDBC or ODBC. I can come over, cross the pond, and all of a sudden I'll be writing Hadoop applications, right? That just doesn't happen, at least now. Okay, so this leads to this quotation, right? It's not enough to build a scalable, stable system, but the system also has to be easy enough for thousands of internal developers of all kinds and types to be able to use it. Okay? This is not a quotation from me. I'm not smart enough to make remarks like this. I stole it from someone. So I stole it from Arun Jacobs, who's the data infrastructure team lead at Disney. Okay? So that's an interesting point, right? This is the diagram we saw earlier. We saw this is a common infrastructure that people use for developing applications on Hadoop. It's 100 to 1. But I claim that Hadoop is complex, flexible, sure, but complex and low level to work with. And why do I say that? Because if you zoom into this, you've got a little more broad things here. Okay, so you've got, on your web application, remember this is stuff you wrote, you've got a servlet that runs in a servlet container that writes logs on a log4j appender, right? So you essentially have a log file that you're populating with clicks and whatnot. Then you use this thing called Flume, right? This is Apache Flume. It's an Apache project that's used to transfer data, to stream data into HDFS, which is this guy right here. Okay? So Flume essentially will read, listen to the log4j file, and it will transfer data to HDFS. Okay? You store your event data in HDFS. You run a MapReduce job on top of that. Okay? And this runs every hour. By the way, many people feel that MapReduce jobs are pretty taxing to write, because at the end of the day, they're Java code. So a lot of people resort to something like Hive, which is up here. Hive is a SQL engine, so you write SQL queries, it will compile them into MapReduce. At the end of the day, you're still writing MapReduce jobs, running MapReduce jobs on the cluster, but the way you're running MapReduce jobs is not Java or Python, it's a SQL declarative syntax, right? All right, you also need this workflow engine. And this is kind of like a fancy cron job, right? You need to tell that you run this job every hour. And well, wouldn't it be nice if the cron job was aware of the things in the Hadoop ecosystem so it can put things on the class path and run them, right? So Oozie is that thing. It's again top level Apache project, so that's Apache Oozie. And it's a workflow engine. So it will, I'm sorry? Okay. It will kick off jobs every hour or every 5 minutes, every 15 minutes, whatever the case be. And you can do things like run my Hive job every 10 minutes. If it fails, run B, otherwise run C, right? All right, so this is our sort of zoomed in view of the diagram there. Let's zoom in a little more. Okay, so you've still got the web application. You've got this log4j appender, but when you send the record, you send it as a structured Avro entity. Okay, what do I mean by that? Structured Avro entity. Anyone know what Avro is? Show of hands? Okay, want to help me out? What's Avro? I'll put you on the spot here.
Serialization framework.
Right, okay, very good, thank you. So Avro is also Apache Avro, by the way, is a serialization framework, right? So it's a way you can talk amongst different machines, you can serialize things, but also a way you can serialize things onto disk and deserialize them back onto memory, right? Okay, so why do I need this? And the reason lies here, actually. So let's go here. What's looking here? Okay, so you have your event data. Remember, this is data that Flume's going to put on HDFS. Okay, I created these partitions. Now, why are they relevant? They're relevant because when you have, say, 4 years worth of data, when you do a query, maybe you do a query only in 1 year at a time, right? You're only interested in customer profile. So if you're a credit card company doing fraud detection, maybe you're only interested in profile for each calendar year, right? In which case, if you dumped all your data in one directory, by the way, HDFS is Hadoop distributed file system, so it's just like, you can think of it as an abstraction, just like a file system, right? It's distributed along multiple machines, but at the end of the day, it's just a file system. So you have directory structure, you have permissions, you have ownership, users, groups, same stuff. Anyway, so if I dumped all my data in one directory without any indexing, if I ran a query, it's going to query all 4 years of data, right? If I were to put this data in subdirectories, by the way, partition is just a subdirectory, and I queried that particular year, it's only going to query 1/4, because it's only going to query that particular subdirectory, right? All of a sudden, the I/O you have to do to run that query is 1/4 of what you had to do if you dumped all your data in just one directory, right? So that concept is called partitioning. And so I was talking about why Avro schema needs to define that, is because there is some record, there's some part of your record that knows, that contains information about what partition it needs to go in. So in our case, maybe the record has a timestamp. From that timestamp, we can figure out what year it belongs to. Based on the year value, I can put it in the appropriate subdirectory, right? So I can put it in one of these n partitions. Okay. But if I have to extract that timestamp from the record, I need some schema on that record, right? Okay, let me not conflict this with the idea of schema on read and write that Hadoop does, right? Remember, Hadoop is always schema on read? Okay, so I'm not putting a schema on my data. For the purposes of just figuring out what partition it needs to go in, I am applying a schema temporarily while I'm transferring the record here. Okay? Too much detail that you probably will ever need. Anyway, the thing is, you need to define the schema, and then you need to run a Flume agent, which will take that schema, put it in a file channel. File channel is where you store the records temporarily while you buffer them before they get to HDFS. File channel means they get stored in a file on disk, on wherever the Flume agent is running. There is a memory channel where they get stored in memory while the buffer is being filled. And then you have a data sink, right? And this is a special data sink which will write data onto HDFS, but also populate some metadata. Okay, what's metadata? Metadata is information about your data, right? So if you have log lines, you may have, if it's a CSV file, you have all these columns that you can think of in your data, right? So maybe the first column is timestamp, the second one is IP address, the third one is a cookie. All this information can be used when you're running this MapReduce job right here. Okay? You can also put information in the metadata on what year and what partition directory that year corresponds to. So you can say partition N is 2014, partition N1 is 2013, and partition 1 is 2000, right? That information can go in the metastore, which can then be leveraged by Hive and MapReduce to only query that specific partition, right? Make sense? Okay. So someone needs to populate that metadata as record comes in, and the best person to populate that metadata is the person syncing that data into HDFS, right? Because when it gets synced, it may have to create a new directory here, a subdirectory. If it sees the record for 2014 for the first time, it'll go create a directory here, but also add a partition entry here saying there's a directory for 2014. Okay? All right, and then you still have Oozie up here. Okay. All right, this is super complicated, right? Why am I telling you all this? Because today, if you were to use Hadoop just the way it is, well, you kind of have to know all this, right? You have to know that there's a Flume agent. You have to know about this concept of intercepting a record, taking out the timestamp from it, figuring out the year, putting that data into HDFS in the appropriate directory, also creating a metadata entry in Hive Metastore, and then kicking off a Oozie job to run a Hive query, which will then run a MapReduce job, right? What do you care about? Well, I only care about getting data from A to B. A is my application. B is that final aggregated data set, right? That's what I'm going to use in my aggregation system, in my BI application. So all I care is like taking data from A to B and using it later. So why is there so much complexity, right? All right, well, we're not done yet. So you have to also think about all these details. You have to think about serialization. Remember, HDFS is a file system. So you have to think about what format am I writing my data in? Your log files may be gzipped Apache logs, so they are text files. Do I just dump them in HDFS just the way they are? Or do I convert them to some other format? Should I use a columnar format where columns form a sequence instead of it being a very row-oriented, which is always the case with log files. When you generate log files, they're always row-oriented. Does it make sense for them to be column-oriented when I put them in HDFS, right? You have to think about compression. Is gzip the right compression for me? Should I use bzip instead? Should I use snappy instead, right? Why should I use what? Okay, you have to think about metadata capture. Every time you create a new directory on HDFS, you have to put an entry in the metastore about that. You have to know when to create a new directory in HDFS. Well, lo and behold, if you transfer your application from one time zone to the other, all of a sudden your timestamps are off and your year calculations are off and all the data that you put in metadata and metastore is just completely bizarre, right? Okay, you have to think about data set and organization, right? Partitioning. When you create those subdirectories, should you follow a particular naming structure? What structure would Hive understand? Okay, you have to think about durability and delivery guarantees, right? So here, you have to think about what happens if this guy dies in the middle of transferring a record, right? Does my record get transferred only half? Does it not get transferred at all? What happens if this guy dies in the middle of reading a file, right? Do I lose half a file? Do I get 2 copies of the first half of the file? Right? So all of this has to be done by the application developer. All right. And I would argue you don't need to do this, right? I mean, you don't do this in Oracle and other MySQL and Postgres databases. Why should you worry about this in Hadoop, right? So wouldn't it be nice if Hadoop was more accessible to the enterprise developer, right? That there was some sort of library that addresses common use cases, that codifies expert patterns, right? These are the best practices. That says that most people who do analysis X store their data in Avro files, or sequence files, or Parquet files, or other columnar format files. And most people who do X use Snappy for compression, or bzip for compression, whatever the case be. By the way, no one uses gzip, and there's a reason for that. All right, so it lets developers focus on business logic, not plumbing and infrastructure. And it makes smart platform default choices, right? So it figures out on your own what the default compression codec to use is, right? If you want to change that, there's an API to change that. But at the end of the day, our goal is for you to not worry about what compression codec to use. If you start caring about what compression codec to use, sure, go ahead, change it, right? So the API abstracts away the details while still giving you the flexibility to swap things around, okay? One would argue that when you put a veneer on top of something, you're using that as an abstraction, you're disallowing you from doing certain things that you could do with a low-level API, and that's very true. If you care about mucking with those intricate details of Hadoop, don't use the system, use what's underneath, right? I haven't given the name to the system yet. I'm just setting the stage, okay? So this system is not going to replace anything, right? You still have your Hive, you have MapReduce, you have cascading, you have Crunch, you have all these things that exist in the ecosystem that you use for doing various different things. You just put an abstraction on top of that so you don't worry about the things that most application developers shouldn't worry about, okay? All right, and that thing is called Kite SDK, okay? So what's Kite SDK? It's an open source collection of libraries, guides, and examples for building data-oriented systems, right? Data-oriented systems, as in systems that are based on Hadoop. It provides a higher level abstraction. Most importantly, it supports piecemeal adoption, right? So Hadoop ecosystem has products that are built on top of Hadoop. These are things like MapReduce, Hive, Impala, Search. There are things that are built on side of Hadoop. These are components that integrate. So example of that is Flume, that brings data into Hadoop, Scoop, that brings data in and out of Hadoop, and things of that sort. Other interfaces like JDBC and ODBC also fall in this category, right? So the point I'm trying to make is that in your workflow, you may only be using some components in the Hadoop stack, right? You may be using some components that sit on top of Hadoop, some components that integrate on the side of Hadoop. And it's important that we don't give you this big monolithic bundle and be like, put this on top and use it, right? You only download or use whatever you want to use about the applications that you care about. Everything else, you forget about it. All right. So the way we do that is we divide this SDK in modules, okay? So the first module is called the data module. And what does this do? It creates a logical abstraction of records, right? So think databases right now. You've got Postgres. There's a record, right? There's a record in Hadoop land. When you use Kite SDK, there's an abstraction called a record, right? You create an object. Whatever fields you used to have in your database object, you're going to have them in your record, okay? In Postgres, a record used to exist in a table, okay? The equivalent of that in Kite SDK is something called a dataset. Dataset is just like a table, right? In Postgres, a table exists in what's called a database. MySQL calls it schema. Maybe I'm getting it the other way around. But here, you have a repository that contains a dataset. Okay? So you have a repository. Underneath it is a bunch of datasets, and each dataset contains a bunch of records. This abstraction is provided by the CDK, or the Kite SDK module. And so what does it take care of? It takes care of you providing, when you want to write something to HDFS, you create a writer called dataset writer. You take this object, which could be a POJO object, or it could be an actual object. that you populate from, say, an Avro schema, you pass this record to the writer, right? You say writer.write object, and it will take care of the write, right? It will take care of which directory this thing needs to go in. If there's any metadata that needs to be populated for this record, that also gets populated. So all that is abstracted away from you. You don't have to no longer worry about, well, extract the timestamp, try to figure out the year, create a new directory if it's necessary. Okay? So we'll see the code for that in just a second. Maybe it'll become clear. It'll also do automatic compression, right? We have some idea, based on our customers, at Cloudera to know what compression codecs work very best and what compression codecs are the best supported for particular types of use cases. So this will do automatic compression. It will do file directory and layout management, which means it will create those directories for you, subdirectories for you in the data set, and put the things appropriately there. And it has a metadata interface, so it can upload metadata and change and edit metadata based on what you're writing to the HDFS right now. Okay, so let's look at some code. Okay, so right-hand side, what will be the output? Left-hand side, the code that generates the output. Okay, so let's actually first talk about the output first. So we've got a data directory, right? Root folder, data directory. This is our repository. Okay, then we have events. This is our data set, equivalent of a table. Inside it, I have multiple subdirectories. There's a directory called user ID equals 0. User ID equals 1 and user ID equals 2. These subdirectories contain these files that are .avro. Okay? These are the real contents of your data, right? This is the big data here, add.avro files. So the file format that I'm using for storing this is not .gz, right? It's not gzip data. It's .avro. Avro is not a compression codec. It's a way of writing files. It's a serialization format. Okay. So also I have this directory called .metadata, right? This is a hidden directory because it starts with a dot. And it contains some information about the table, right? Table meaning events. What information does it contain? It contains the schema. It contains a descriptor, which contains some other properties like the compression codec used for storing that data. Okay, so the little detail that I glossed over was typically you store the metadata in an external system called the Hive Metastore so other people can access it. But sometimes, if you don't feel that there's going to be any other application than the MapReduce job that you're writing to access it, you can store the metadata right beside it, which is what I did here. So I'm storing the metadata here, the metadata provider that I used. It's a plugable provider infrastructure, so you change the metadata provider instead of storing stuff to Hive Metastore to just store it on the local file, on the HDFS file system. Okay. All right, let's look at code. So first thing I do is create this thing called repository. Its code name is dataset repository. The variable I assign to it is repo. I create a file system dataset repository, which means this needs to exist on HDFS. It's just /data. I give it a path. You see that? And then I create a new file system handle with some new configuration. I get that handle. This is my repo, right? The next thing I do is I create a data set in that repo that's called events. And then I use a builder pattern. By the way, there was a builder pattern here too. In Kite SDK, we love builder patterns. We assign a schema to it. Well, I don't see the name of the columns or types of the columns. Actually, it's stored in this file called event.avsc, which is a simple sort of JSON-looking block that says column 1 is named blah, or ID, its type is integer, and so on and so forth. Then we say partitioning strategy, okay? Remember, this is the thing where we talked about like picking out the timestamp and finding the year from the timestamp and then throwing it in the appropriate subdirectory. My partitioning strategy is hash, which means I pick some part of the record to apply a hash function on it. Then I modulo that with 53. There's no reason why I chose 53 here. It's your business requirement, whatever you want to choose. So now I can partition my data into 53 individual buckets, right? The result will be between 0 and 52. Based on the result, I will throw that data in an appropriate bucket. And so I get that, right? And so when I'm writing a record, I create a new writer instance, which is events.getWriter. And I create a new generic record. So the way I build a new generic record is provide this a schema. Well, the schema was the same schema that I stored in event.avsc. By the way, AVSC is Avro schema file. Then I set the user ID in there, and I set the timestamp in there, and I build that new record. If I were to write this record, all I do is writer.write. Okay. So if you have written to HDFS before in a real MapReduce job, this is way easier than what you would do otherwise, right? You don't have to worry about doing the hash yourself, then comparing it if the directory exists, putting it in the directory, maybe creating a metadata entry. This is all you do, right? And so if you were to change the partitioning strategy tomorrow, you just change this to, instead of a hash function, you just use an identity function. In our timestamp example, this would be a division function, right? You say timestamp divided by whatever, and you will figure out the year that way. You know, plus or minus 1970, whatever. So this can change easily, and you'll change your partitioning strategy. If you were to use a different schema, you can just change that event.avsc file. If you were to use a different compression codec, you can also add, so this builder has an entry.compression whatnot. You can change that to use your custom compression codec. Cool. Any questions there?
Yeah.
Yes, go ahead.
When you change your partition strategy, does that also apply to old data?
Okay, so the question was, when you change your partition strategy, does it apply to old data? No. It only applies to data going forward. That's why it's a bad idea to change partition strategy in the middle of a data set, right? So you have to rejig old data to follow your new partition strategy. Also, you had to modify the metadata to reflect that partition strategy. Also, partition strategy is not something you change every second day, right? It's a very sort of architectural decision. The same thing that you don't change every other day is something like a compression codec or the schema of your table, right? It's possible, and if you do that, you have to reject data in HDFS. So in this case, you will have to change the name of these directories, right? So user ID, why is this user ID? Because, well, my partition ID here is user ID. That's the name of, also the name of the column which exists in that thing, right? So if you change your partition, you have to rename all these directories to something else. Obviously, the data in here will not make any sense because if you're partitioning now by a different column, let's say ID, the data here is partitioned by the hash on user, well, what would we partition? User ID, right? So if you were partitioning by a different column than user ID, say the timestamp, the data here makes no sense. So you have to essentially create a new data set and read from the old data set and copy over to the new data set. Any other questions? All right, so there's another module that we should talk about. It's called the Morphlines module. It was born out of this open source project called Cloudera Search, which is Solr put on top of Hadoop with a whole bunch of nuts and bolts, right? So you can index your incoming data and streams and store those indexes on HDFS. And essentially you have searching capability on all data that's stored in HDFS. So you can do real-time indexing as data comes in. So there's a Flume sync. Flume is the same thing that actually stores the data in HDFS that can index data as it comes in. But also you can do batch updates to indexes if you have past old data that you want to index. Anyway, so what is Morphlines? It's something that was born out of that project because we needed the capability to have a configuration-driven transformation library. Okay, what does that mean? That means you define in some file somewhere that every record that comes in through the stream should be transformed this way, right? And we thought that was a general functionality that a lot of people use, right? So an example of that, if you are that same e-commerce company, or let's say you have a website where people come in, and you may have some extra information, auxiliary information that you need to add to your records, right? That could be, if the person is a customer, you can relay that cookie and connect it to a user ID, right? So you want to append that user ID right beside that record. And the way you do that, you can leverage something like Morphlines to add auxiliary information to your records. Does that make sense? It's very rare that you will use the record the same way it is. You have some auxiliary information you want to attach, and Morphline is a very good tool to do that. It's bundled in a module here. All right, there are other modules. There's a Maven plugin which can allow you to package, deploy, and execute your custom applications. And there are other things that we have. So there's integration with Crunch and MapReduce, which means it's easy to write cron jobs. Crunch is kind of like cascading. It's a library that allows you to run workflows on top of Hadoop. And then there are administrative tools and operations you can do. The records that we created, so if you go back, the record we created here was created from a schema, right? And I call that generic record. But you can have a Java object, plain old Java object associated with that, and you can just pass that to the writer, just like we did with the generic object, and the writer knows how to write that to disk. All right, what else do we have here? Okay, so feature. So in Hadoop land, you can store your data in HDFS or in this thing called HBase, right? HBase is built on top of HDFS, but it's a storage handler. So HDFS means you have slow random reads and writes, but fast scans. And HBase usually means the other thing around, which means you have fast random reads and writes, but slow scans. Okay. So the Kite SDK support right now for HDFS is fantastic, right? Everything we did, we threw data on HDFS. We didn't really talk about HBase. And we created tables, we analyzed those tables, we do analytics on them. Most of the queries that we did were also batch oriented, right? Every 15 minutes we ran a job. Then we analyzed that, we populated this other data set, which we put our BI application on top of that. But there are obviously use cases where you want to use HBase, right? Where you want to just take, here's a user ID, get me the record, right? And so HBase is an open source project, so it's Apache HBase, and it's built after Google's Bigtable. So we want to add more support for HBase in the future. We have higher order data management, so things like if you have multiple files within a directory, right? Let's go back here. You had multiple files in that directory. You had 2 files. Why was that? Well, because maybe the buffer that you were using, remember that there was a file channel in Flume. The buffer may have a certain length, and once that buffer gets full, it will persist that to HDFS. So you had to do it twice. But maybe it makes sense for you to compact these files together, right? So we want to add functionality where you can do background compaction and conversion of formats from one format to the other if that's allowed by the API. And then we want to integrate with other middleware components like Spring Source and things of that sort. One thing that's not on the slide, but also on the mind of the developers of SDK Kite, is to allow things like exclusive read share. So there are often cases when all you want to do is just share a file for reading, or you want an exclusive lock on that file for writing, and no one else should be writing to that file. Right now, you have to manage that yourself, right? Your application has to be aware of that. So we are trying our best to abstract away these things that you typically don't do in traditional relational world, but you end up doing a lot in Hadoop, right? So we are trying to move away the level of abstraction so you don't have to worry about, all you worry about is writing code, right, for your application. All right, so, well, this is all great, but what if I want to use it? Here's all the information you need, right? So the docs are there, examples are there, and the source code is there. It's Apache ASL v2 licensed. And the belief here is that unless you publish examples, and these are not hello world examples, these are, remember the 3 use cases that I talked about, and the use case we went through in this example, in this presentation? That examples like that are up there, right? So these are real world examples, because all we want to do is just take problems from real world, because the existing low-level interfaces already allow you to solve all these problems. The idea is that for the common use cases, we codify the best practices and just not have to worry about the intricate low-level details. All right, you can also download Kite's binary artifacts from Cloudera's Maven repository. You can build them on your own if you so desire. If you have any feedback, please, I would really appreciate that you get in touch with me over Twitter. Let me know what you liked about this presentation, what you didn't like. And I have already posted the slides up there. So you can download the slides there, but I will be giving the moderator a copy of the slides as well, so I'm sure they will have them for you. And that's my LinkedIn. I'm writing a book with O'Reilly upon architecture. So if you want to follow more details on when the book will be out, there is a Twitter handle, Hadoop Arch Book, ARCH book. And then there's a website for that as well. The goal of the book here is that, well, CDK, this Kite SDK thing tries to help you out, right? But there are still decisions that some data architect or a developer in the organization needs to make, right? The decision is, should I store my data in HDFS or HBase? Should I use Flume or Kafka or Scoop, right? Should I use a columnar format or a row format, right? An automated tool necessarily can't figure out what format is best for you, right? So the book is actually a use case-centric book which talks about why would you make decisions like those and how would you make decisions like those in your Hadoop use cases, right? Cool. And that's all from me. And we have 10 more minutes, so you can ask me any questions that you may have. Yes, sir. Right. So the question was, what about Apache Pig? And I'm going to go back here. Okay. So you see Hive here? Yeah, we can just replace that with Pig. Pig is very similar to Hive. It's a top-level abstraction. In Hive, you write a SQL query, and that translates that to a MapReduce job. In Pig, you write what's called Pig Latin, and that's a workflow language, and Pig Latin gets transferred and compiled into a MapReduce job. So similar idea, just the way you interact with these components is different. Pig support also exists just as well in Kite SDK, just like Hive. Other questions? Was that clear, huh? You sure? You have 10 more minutes. I mean, there's no fun in going out. All right, I guess we'll have to leave. Thank you, everyone, for coming. Enjoy the rest of your day.